Thank you everybody for coming. So we will talk about explaining machine learning models because it's something that we have to use in our daily work. So who are we? So we are a team dedicated to data science at AXA, which is a global insurer company. We are mostly Python and scikit-learn users, meaning that we are not taking machine learning from the academic perspective, even if we like it and we like going deep into the details. But we are mostly users, and as it was said, scikit-learn is a good compromise between academic and industrial machine learning. And as it's very easy to use, it's a choice of evidence for us. We like problems, we like questions. You will see here some questions we have. Maybe we don't have the full answer, so if you have any ideas about our problem, just feel free to ask questions or to help or to contribute. And we participate to some data science events, like we publish Kaggle competitions, we organize meetup, and we also, of course, sponsorize PyData today. So why explaining machine learning models? As it was said, predictive models are everywhere today in our society. So just to give a few examples, for example, if you go to the bank to have a loan, an algorithm may be behind the scene evaluating or rating your person. And sometimes, as a banker, you want to explain, for example, why a loan is refused. Maybe the machine said, I refuse, but you have to explain it, and maybe to see with your customer how to arrange things to make that you have your loan. Another example is, of course, fraud detection and anomaly detection. For example, we can have predictive algorithm that trigger alerts, but when you have a suspicion of fraud, it is very important to be sure that you have a fraud, and maybe you have to make deeper investigations or forensic on what is happening. So the machine has to tell you the clues and why it thinks that it is a fraud. Last example is, for example, employment and jobs recommendation. Some algorithm now can help you and help unemployed people to suggest new jobs, sometimes not at all in the field of the original job. So of course, this is also helpful to explain maybe what are the skills you have that may be used for another job, and maybe the recommender system captured something that you have also to explain to be more precise with your customer. As it was said, also our society will become in the future automated. Predictive algorithm will be everywhere. Some people even say that maybe it's the end of the humanity. And there are some laws that are appearing. Maybe it's not today the fact, but some recommendation, for example, from the French Conseil d'État, who said when a decision is taken by an algorithm, the algorithm has to explain to the human why this decision has been taken, so that the human is able to understand the decision and to accept the decision with all its mind and all its understanding. So what do we want actually is slightly different, because explaining models is something that we see a lot. We can explain model on a population basis, meaning we can explain why this class generally was predicted as its class. So at population level, there are solutions, but what we want is to explain one particular observation. and maybe two different observation A and observation B, which were predicted in the same class, maybe they don't have the same explanation behind the scene. So ideally, we would like a system that help us to explain what these two different observations have been predicted in this class. So let's give a toy example, a bit like the hello world of machine learning with not the iris dataset here, but the Titanic dataset. You know this dataset where we have all the passengers of Titanic, and we have to predict did the passenger survive or not. So it's a well-known dataset. Here we have almost 900 passengers, and we can train a model on it with scikit-learn, and we can have a look at the feature importance. And here we can see that the age and the fare and the sex is important for the prediction on a global population point of view. And indeed, if we see on sex, we see that 20% of male survived, only 20%, and more than 70% of female survived. Now, what we would like is when we run our predictive models, for example, of the female populations, sometimes the algorithm will say this female survived, which is the trivial prediction because most females survived. But there are also some females that are predicted as not surviving. So the model captured something for this particular female, saying to us that it was not surviving, which is not the common case of female. So the question is why made this algorithm decide for this particular female passenger that it didn't survive, and which is indeed the case, and which is not the usual surviving rate of this person. So if we have a simple case like linear models, what we can do, as you know, linear models are an accumulation of coefficients. So you have the beta coefficients, which are the weights of the model. On a population point of view, so the beta coefficients are not the one that we are interested in. What we are interested in for each observation, it's the product between beta and x, the features of the particular observation. So here, in yellow, we can see for an observation one, what made the model predict this prediction. And on another observation, we can see another repartition of the beta x, so we can understand how did the model made its prediction. So only in a linear model, we could say that on observation basis, we can differentiate one prediction from one other. Unfortunately, if we complexify the model, then we lose in explainability. So in scikit-learn, now we will focus on random forest, which are more powerful algorithm, but also less interpretable algorithm. So we have this feature importance callback, which help us to see on a population basis what are the most important features. But again, it's not what we are looking for, because we are looking at observation basis. So I think it's your turn now.
Okay, so so the question of interpreting actually is a very complicated question, because the definition of what interpretation is not really clear. And so it's kind of difficult, because we are trying to make something, and what we are trying to make, we don't know exactly what it is. And so if we look at the specific example that we are focusing on, which is explaining one single point inside of a space, there are different things that we could try to do. One would be, like, for example, to do a what-if explanation. So let's say we have this client, and then he has these variables, and then we say, okay, what if this variable is different? So we change the variable, and then we say, what if this person was not a woman, but was a man? So what happens, how your score changes, or how your classification changes? The thing is, we didn't choose this one because it becomes very tricky very quickly, because imagine you have zip codes for deciding whatever. And so what if I change the zip code? And so what does it mean that, like, I want to estimate the revenue, and I know he lives in Lausanne, right? So what does it change for me? So the metric in the categorical space is a kind of difficult to go from one part of the other. Then we can think about interpreting. So what does interpretation mean? We could think about looking at the, let's say, sensitivity of the variable. So if I move a little bit this variable, what happens? So we would like to look, let's say, at something that is close to the derivative. So the problem with this, so we didn't choose to explore this path either because the derivative is extremely local, right? So if we look at the decision tree, we have a lot of flat spaces, so we cannot derivate. But even in the case of the random, we have this reduced problem, but we still have it. And actually, the derivative have also this problem that we will predict very locally. So imagine you have a prediction that says, oh, if you do this and that, we will give you a loan. And he does this, but actually the real curve is not monotone, because actually when we do this prediction, we will do this random forest, we will want to also grasp non-monotone behaviors. And then we give this advice, let's say, or this sensitivity, and then actually it's not true, it's only true on this very, very little place. So we didn't choose to do this either. And so we try to look at something which we call the feature contribution. So there are different ways of looking at this feature contribution. And the one we look at is to try to do something like a path approach, to go through all the paths of the decision that has been taken. And inside of this path, try to quantify something. And this something will give the interpretation. So one thing you can do is, okay, well, let's say we are here. So you are the client here, and you have been classified or whatever. And then you will look through all the trees, which variables, which features have been used in order to give you this decision. And we make the hypothesis that more this feature has been used, it means this feature is very important in your case. We can weight this also by using the impurity, for example. This is pretty simple to do. And so you could weight and say, okay, well, here, this split, it was very important, or had a very strong impurity gain, so we can weight it and then say, okay, these ones are more important, and so on. So this idea is a little bit around, so we have seen this in some papers. For example, in this paper, which is about pharmacy and biomolecular sciences application, and it's a very similar idea. The difference, let's say, of what I said just before, is that we will look, for example, we are here, so we're going to follow the red path for one tree, and so we're going to try to explain why there is a score of this, or 23. What we are going to do is we're going to look at the difference of the score which you would have if you were here, the score that you would have if you were here, and so on, and you will look at the difference. And you will get some explanation of this form. You will have the prediction as 2260 from the trend set mean, minus 2.62 because of the loss from ERM, and then plus 3.52 because of the gain on whatever. Okay, so this is a very, very nice way of doing this, but it's a little bit tricky to program this in scikit-learn. So we haven't implemented this one yet, but we implemented the one that I just explained before. The number of times a feature was selected, and the number of times and weighting this with the impurity, right? Okay, so we'll show you some Python notebook. Yeah, and then afterwards I'll come back a little bit more on these limitations that we would like you people here to maybe improve or help us improve.
So, okay, so this notebook is just to illustrate our problem. So we use the Titanic data for that. As usually, what we do is to create a first model based on a random forest. So, by
Increase the? Oh, the size of font, yes.
the size.
C'est CTRL plus, c'est ça?
Sinon, tu veux zoomer le.
Ouais. A bit more? Okay, so what we do first is to import our libraries and build a model. So this is what the data looks like. And we decided to only select 7 features that seems to be important. So the class of the person, the age, the number of siblings that the person has, there's the fare, the sex, and the location where the person did embark it.
Well, the part is the number of parents and daughters and sons.
Next step is to split our data frame between a training set and a test set and try to fit our model on the training set. We after that have our resulting scores, and we see that if we are looking at the performance of a model, the model is quite good because we have a AUC of 0.87. So just to summarize a bit, what we are looking now is the feature importance of the the whole population, which is not what we are looking for, but is just to fix some ideas. So what we can see now is that the sex, the fare, and the P class are very important on a population level. And some others seems to be less important, like the part, the siblings, and the location where the person did embark it. So these are some simple descriptive statistics that Christophe has already shown you. And now what we are trying to do is try to understand prediction at the observation level. So what we do first is to build a data frame regrouping features, ground truth, and model prediction. So you can see the scores here, the ground truth, and the features that we have used. So now what we are trying to do is to see what happens with the person who have the highest scores and person who have the lowest scores. So woman. And only for women. So this is the woman with the lowest scores that our model predicted. These are their characteristics and the truth and the scores. And we do exactly the same thing with the women with the highest scores. Now we start, what we have tried to do is to implement a very basic first method where we count how many times did an observation pass by a given node in all trees. So this is a function, so I won't, it's kind of complicated to explain it right now. But what we can see is the results. So for the highest, for the woman who has the highest scores, what we can see is that let me see, the fare, the sex, the age, and P class seems to be very important. And when we try to do the same thing with the woman with the lowest scores, we can see that, well, these the variables that seems to be the most important are quite the same. So you have again the fare, the sex, the age, and the P class. So ranking these variables makes it easier to read. So as I said, the fair edge P class seems to be very important for this group of person. But the problem is that we see quite the same variables for the other population. So what we see here is that we are not very satisfied by this first method. So what we have tried to do is to take into consideration the impurity of each node to see if we can see some differences. So we did exactly the same exercise. Instead of counting the nodes and the variable for each node, we sum the impurity of each node. So you have here the result for the woman with the highest scores. And what you can see is that fair, sex, P class, age are still very important. We do the same thing with the lowest impurity. And what trying to read this is kind of complicated. So what we did is to rank them so we can make the reading easier. So what we can see now is some few differences because age comes first for the person with the highest scores. Then you have the fair, the class, and the sex variable. And what you see here is the results for the lowest scores. So what we can see now is that the ranking of the variables have changed with the previous method, but we are not still satisfied with this method, and that's why we wanted to continue our work by adding the population included in each internal node. Unfortunately, we don't have these properties in scikit-learn because in scikit-learn, each node doesn't store the values of each categories of person. So the work is still under progress. And we wanted to ask the community what they are thinking about these two basic approach, which seems to show some very first results, but which are for us not good enough to present to our business teams.
Okay, so we can maybe come back to the slides. Oh, actually, so this is what we did. So we have done transversing trick using trivial metrics, which is adding +1 when feature is crossed, and then doing some weighting when we have a feature is crossed. So as being said, there is a limitation on having information on the number of samples of each node, and actually we need a lot of things, and I will come back to this in the next slide. Is that there is we would like to have more information at the node level, because actually what happens is that when we want to do this in interpretations, actually interpretations, as we understand, comes down to comparing people, right? So why my thing is more expensive than it was before, or why I'm paying more than my neighbor, or whatever. So it always comes down to these comparisons, right? And in a tree, we're in this nested setting, right? In which we are, let's say, Mr. Smith or Mrs. Smith. And then we have, at each split, we're going to have a population, and then we're going to have a small population, and so on. And so what we really need to have in a nice programming environment is access to some measurements that allow us to compare the sets, so that we can have, for example, average score here, and then we want to make the difference of the average score here between this and that, for example. Or let's say average price of this population compared to average price of this. But then you can do other things. For example, I want to see what happens to the people who are in the oil leaf. Like, I want to compare this population with the population which is in the green circle but is not in the yellow one, right? And so this is really like a thing that we are going to implement. But if you can help us with that, it would be really, really great. So thank you very much. Oh, yeah, and so this is the things, just to say, I thought this was the end. So these are the kind of things we would like to have. Number of classes is 0, number of 1, node of size, average score, and so on. And then we'd like to do some metrics on each node. Okay. So thank you very much for your attention. And so we're open now for questions. If you want to join by doing this in open space, you can do it either on your own, but you can also contact us if you are interested in such problems because of course we're hiring very smart people. So if you're interested, contact any of us and you can solve these problems also in AXA. Thank you very much.